the final homework problem, problem 1482, once again gives us 3-step mechanism, a fast in equilibrium, a slow, and a fast one. And the series of questions begin with what is the overall reaction? And again, the overall reaction is found by eliminating things which appear like this, and then before the end of the reaction, disappear. So pH3 appears and disappears. CH33AU appears and disappears. Oh, did it in the wrong direction. There's where it appears, and here's where it disappears. So the things which persist, which stick around, don't get crossed out. So this one gets crossed out because it shows up and disappears. This one gets crossed out because it shows up, then it disappears. This gets crossed out because it's formed in this step and consumed in this step. So I'm just left with these 3 parts. My original compound decomposes into these 2 parts. That's my overall reaction. I find it by eliminating all of the intermediates. Right? Following it up by asking what are the intermediates, it's all the things that I just crossed out. So these are my intermediates. They're all created in one step and consumed in following steps. So they are the intermediates, all 3 of them. The molecularity, remember, you can find that on page 535. And again, it's based on how many molecules are involved in each step as reactants. So only 1 molecule for the first one, that makes it unimolecular. Only 1 molecule for the second step, that makes it unimolecular. But 2 molecules for the final step, that makes it bimolecular. So step 1 and 2, unimolecular, and step 3, bimolecular. The easy question again, what's the rate determining step? Okay, find the slow step. That's the rate determining step. Easy as that. Whichever one is the slow step sets the rate for the reaction. So to get to the rate law, we just have to do the rate law for the slow step, but it cannot have an intermediate. So initially, this looks like rate equals, oops, didn't expect that to happen. Okay, the rate equals K times the concentration of this molecule, but it's an intermediate, so we're going to go backwards 1 step where that intermediate was formed, and we're going to use the fact that it's in equilibrium, that there are 2 reactions of equal rate, one going forward and one going backwards. So this concept gets us through any problem that has an intermediate in the slow step. And we can see that the forward rate has to be K forward times the concentration of the reactant, but the reverse has to be K reverse times the concentration of the 2 products. This product right here, that's the problem in our slow step. The rate law for our slow step is done in terms of this molecule, and we can't use it because it's an intermediate. So I set the forward and the reverse rate equal to each other. Now I need to isolate this term, the one that's our problem, So that means I'm going to divide both sides by Kr and both sides by pH3, concentration of pH3. And I get Kf over Kr times the concentration of the first reactant divided by the concentration of pH3. That'd be called phosphorus trihydride. And that equals the molecule which is in my slow step rate law. So I substitute in. Remember, this is my slow step rate law. If I substitute my new number, right here, this whole big thing takes the place of this whole term, I end up with all of these K's, which can be combined, times this concentration fraction. So I could write it this way. There's all my K's are now combined into one K. And here are my two concentrations. This could also be written this way, with 1 over the concentration of pH3. They are identical. The final question, after I determine this rate law up here, is what would be the effect of adding additional pH3 to this? Well, all of these are numbers. There is a concentration. So if you added a bigger number into this fraction, that would have the effect of lowering this number. So increasing pH3 will decrease the reaction rate. This compound has an inverse effect on rate. The more of it that you find, the slower the reaction goes.